The objective of measuring gravitational acceleration are to investigate the functional relationship between height of fall and falling time and to determine the acceleration due to gravity by studying the motion of a freely falling body. The theory of this experiment is, if a body of mass is accelerated from the state of rest in a constant gravitational field, it performs a linear motion. By applying the coordinate system in the way that the x-axis indicates the direction of motion and solving the corresponding one-dimensional equation of motion, we get the formula as shown in this slide. We obtain for the initial condition, which is hash multiplied by 0 equal to 0, and the formula we get is d hash multiplied by 0 divided by d multiplied by t equal to 0. The coordinate hash as a function of time, which is the formula is hash multiplied by t equal to 1 over 2 multiplied by g multiplied by t square. The height is directly proportional to the square of time. This can be displayed by a representation of hash t square. From the regression line of the data, we can calculate the gravitational acceleration because the slope is equal to 1 over 2 according to equation 1.
Apparatus, digital watch, ping pong ball and 100 cm ruler. Procedure. Firstly, the apparatus was set up as in figure. Secondly, the 100 cm ruler was placed on a flat surface and it was held by the catches. Thirdly, the ping pong ball was placed on 100 cm beside the ruler before it was getting dropped by the dropper, while at the same time the digital watch was started until the ping pong ball touched the ground and the dropper stopped the digital watch. Fourthly, the time of the ping pong ball to touch the ground from 100 cm was recorded. Fifthly, the experiment was repeated for 90 cm, 80 cm, 70 cm, 60 cm, 50 cm, 40 cm, 30 cm, 20 cm, and 10 cm.
From the data, plot graph for A. Rate of fall as a function of falling time. B. Rate of fall as a function of the square of falling time. 2. Using the rate of fall as a function of the square of falling time graph, determine the gradient slope of the graph and calculate the value G. 3. Calculate value of uncertainty of G. 4. Calculate the percent difference between the value of G calculated in part 1 above G experiment and the standard value of G standard. What is the percent error in this experimental value? 5. Is there any experimental error discovered? Yes, that is a parallel error caused by a random error. The experiment observed might have misread the data or might have been negligent in their reading of the data. Due to uncertainty, the data value precision and accuracy may be a little off. It may also be due to incorrect computation method or used by the observer, but this can be minimized by averaging many observations.
Discussion of experiment 3. The statistic in table 3.1 demonstrates that the mass of the object has no effect on how long it takes to descend to the earth, indicating that the object is experiencing the motion of a freely falling body. Free fall is the motion of an object falling only against the force of gravity and not against any other external force, such as air resistance. Only gravity acts as an external force during free fall. Without air, any item falling will experience the same constant rate of acceleration. The acceleration caused by gravity can be calculated by measuring how long it takes a body falling freely to cover a given distance. According on the data that was recorded, two graphs were produced. The height of fall as a function of falling time for ping-pong ball is shown in the first graph, and the height of fall as a function of falling time squared is shown in the second graph. If the body mass is accelerated from a state of rest in a fixed gravitational field, according to the depicted graph, it will move linearly. Based on the graph that has been plotted, the gradient and the value of g has been obtained based on the graph height of fall versus t squared. The gradient are searched using two coordinates from the graph and using the formula m equal to y2 minus y1 divided by x2 minus x1. The value of g is obtained using formula given ht equal to 1 over 2 multiplied by gt squared and compare it with y equal to mx plus c, which gradient m equal to 1 over 2g. From formula value of g for ping pong ball is g equal to 9.8 ms negative 2. From all the info that has been collected, the uncertainty of g has been calculated using m equal to 1 over 2g. The percentage difference is calculated using the formula shown in this slide. Based on the experiment and calculation carried out, there are experimental error detected. Experimental error are searched using formula percentage of experimental error equal to experimental value minus known value divided by known value multiplied by 100%. Percentage of experiment error shown in this slide. Parallax fault could be the root of the experimental error. The measurement of the scalar on the stopwatch is misread by the observer. Taking a collection of readings from various observers can help to reduce this mistake. Random mistake may also contribute to the experimental error. The influence of air friction, which only marginally impacts the acceleration rate, might not be taken into account in this experiment investigating the impact of gravity on acceleration. When doing the experiment, make careful to stop any source of air from entering the lab in order to limit air friction. For instance, close the fans and windows. Conclusion of experiment 3. The functional relationship between fall height and time taken to ground was that the steeper the fall, the longer the time taken to ground. Other than that, the acceleration due to gravity by studying the motion of a freely falling body was 9.8 ms negative 2. Next, when air resistance is disregarded, the mass of the ping pong ball has no effect on the value of g.
Here are some references we found, such as journals, articles, and others. For instance, Roger Elman, April 2017, Gravitational and Anti-Gravitational Applications International Journal of Geosciences, Vol 8, Number 4, 10.423/IJG.2017.84025. And Patrick Vaught, 29 September 2012, 16 smartphones as experimental tools, different methods to determine the gravitational acceleration in classroom physics by using everyday devices. European J of Physics Education, Vol 4, Issue 1, 2013, Kuhn and Vaught.
The objective of frictional force experiment is to determine the coefficient of static friction of different surfaces. The theory of this experiment is force and velocity are vector quantities that have both magnitude and direction. Velocity is the speed in a specified direction which is given object is traveling. Force exists when the object accelerates or undergoes a change in its velocity. A body at rest or in equilibrium exhibits resultant force, or the sum of all forces acting on the body is zero. Gravity is an attractive force that exists between two masses. The magnitude of the force depends on the magnitude of the masses. When m is the mass of the object and g is the gravitational acceleration, the magnitude of the gravitational force exerted on an object is referred to as its weight. Normal force is a contact force that acts in the normal direction or perpendicular to the contact surface between two objects. Figure 5.1 shows the free body diagram of a mass lying on a horizontal surface where the normal force is equal in magnitude to the gravitational force. Friction is the force that resists the relative motion of one surface in contact with another. There are two types of friction, which is static and kinetic. Static friction is the friction that acts on an object that is at rest. Static friction is the force that must be overcome in order to move a static object. The maximum value of static frictional force is given in this slide. When μs is the coefficient of static friction and n is the normal force, the coefficient of static friction is a dimensionless constant that depends on the object and the surface is laying upon. Kinetic friction is the friction that acts on a moving object, and the kinetic frictional force is given by Fk equal to μk n, where μk is the coefficient of kinetic friction and n is the normal force. In this experiment, the frictional force between a wooden block and the rubber surface on a horizontal and inclined plane will be measured, and from the plot data, the coefficient of static friction will be obtained.
Apparatus: wooden block with rubber covered at one side, 50 gram masses, 10 Newton spring scale, string, and tabletop. Procedure: firstly, the mass of wooden block was measured, recorded as m. Number 2, the apparatus was set up as shown in figure 5.2. Number 3, the tabletop was made sure stable and horizontal on the ground. Number 4, the spring scale was attached and the wooden block with a string. It was placed horizontally on the tabletop. The rubber side of the block was made sure was faced downward. Number 5, a 50 gram mass was placed on the wooden block. Number 6, the spring was pulled slowly. Once the block was started to move, the spring scale's reading was recorded. Number 7, step 4 until 5 was repeated for 3 trials. Number 8, another 50 gram mass was added on the wooden block and step 5 to 6 was repeated. The step was repeated until a total of 500 gram mass was on the wooden block. Lastly, step 1 until 8 was repeated. The rubber side of the block was made sure was facing upward. The data in table was tabulated. Analysis. Question 1. Draw and label the free body diagram of the wooden block. Question 2. Plot graph of static friction force Fx against normal force Newton and for the rubber surface and non-rubber surface. Question 3. Use the gradients obtained from the graph to calculate the coefficient of static friction for each surfaces. Question 4. Compare and discuss the coefficient of static friction obtained. Rubber surfaces facing the floor have a higher static friction coefficient than non-rubber surfaces. A static object is moved. To move, more force must be applied than there is static friction. In conclusion, the coefficient of static friction increases with the surface roughness.
Questions. Question number 1. How can anti-lock brakes stop a car in a shorter distance than regular brakes? Question number 2. from your experiment which material has the highest coefficient of static friction. Does this agree with your hypothesis? What do you think determines the coefficient of static friction? Question number 3. Once the mass begins to slide, does it move smoothly or does it undergo stop and go motion? Explain the motion.
Discussion of experiment 4. According to the result of this experiment, a rubber band surface will have a greater coefficient of static friction force than a non-rubber surface. The computation and plot graph demonstrate that the coefficient of static friction force for a rubber surface is larger than for a non-rubber surface, proving the prediction to be accurate. The experiment may experience a few errors. By setting the eyes perpendicular to the scale, parallel error caused by error in reading the scale on the spring scale can be avoided. The reading on the spring scale may also be impacted by reader mistake caused by the uneven surface of the table utilized. This can be prevented by measuring the spring scale numerous times and average the result. Conclusion Experiment 4. Due to the inconsistent force in this experiment when pulling the block, it's best when one person pulls the block 3 trials. A bigger and more sensitive dynamometer will be required in the future because some aspects of the experiment cannot be accessed. This increases the data accuracy and reduces its error. To sum up, the force of static friction will and should always be greater than of kinetic friction since it takes more force to move an object than kinetic friction. Thus, kinetic friction only needs to sustain. The frictional force will change when different materials are added, but rolling the block is the best technique to lessen frictional force because it was shown that this method had negligible frictional force.
Here are some references that we have found, such as journals, articles, and others. For instance, an experimental study on the relation between friction force and real contact area, Journal of Education in Science, Environment and Health, also Preconceptions in Mechanics, 2nd edition.
A simple reminder, be proud of yourself because you are doing great. So that's the end of our presentation. Thank you for your attention and thank you for watching.